Well, hello again. Welcome once again to Chapter 9, and we are going to spend an entire chapter in Chapter 9 on spatial thinking. Spatial thinking is basically geometric type concepts. So we're going to start with really simple building blocks, which is what Lesson 9.1 is going to be about. And then from those building blocks, we're going to put them together. We're going to make polygons, things like triangles and pentagons and squares and parallelograms. We're also going to make circles, and then we're going to move to those are two-dimensional objects. We're then going to move to three-dimensional objects, things like prisms and cones and cylinders and and boxes. And we're going to talk about surface area and volume. So that's a quick overview of Chapter 9. And my apologies, if you watch the first 9.1 video, sometimes my iPad, if it gets a notification, it pauses. And I'm sorry I didn't realize that had happened. So my apologies for the abbreviated lesson. Let's see if we can get all the way through it this time. All right, so again, let's start with the basic building blocks that we're going to use for spatial thinking and geometry. And those, as you see at the bottom of the screen, are points, lines, and planes. And there probably should be an S in there. So points, lines, and planes. Okay? And we will define lines and planes, but honestly, points are a little tricky to define, but we're going to try anyway. So let's get started. All right, so let's take a quick look. A point is very much an exact location, and no matter how we represent it, I can use a dot, I could use a small circle. If I zoomed in with a magnifying glass right here, I would see that actually is a lot of points all in that little blue speck in the middle. And so don't get too fixated on the dot that represents the point. We've got to use something to show kind of where it is. But a point has absolutely no area whatsoever. It is an exact location. Okay, so it's not something you can actually draw. Okay. Now, if we take 2 points, let's take the points A and B. And what we're going to do is we're going to consider the point A and the point B, and we're going to consider all the points that are directly between those 2 points, and we get something called a line segment, or sometimes just referred to as a segment. Okay, it is an infinite collection of points. You can get them closer and closer and closer together. Remember that these points are exact locations, so we can squeeze as many of them in there as we want. In fact, there's an infinite number of points on a line segment. Okay, now the notation for everything that we're going to be talking about today is very important, especially for segments and lines. Sorry about that, but at least this time the recording will go on. All right, so we start out with points which have no size at all. Then we build up segments. Okay, so now you've got something that lives in one dimension, and I like to think of this idea of an ant. If an ant lived on a point, it really couldn't do anything. It lives on an exact location. It can't move in any direction whatsoever. Now, if it's on a line segment, it could kind of go back and forth between A and B. It still can't spread out. It can't go left or right, but if it can go forwards and backwards from A to B and from B back to A. Okay, so that's a one-dimensional object. Okay, and any kind of thing that we build out of a segment will also be one-dimensional. Okay, and again, don't forget it is still an infinite collection of points. All right, let's go to the next idea. So take the segment and let the ant not just go from A to B, but let him just keep going in a straight line past through B and go on to infinity. Or vice versa, start at B and go on through A, walking to the left and go on to infinity. And so now the segment becomes a line. Okay, so really 2 points determine a segment, and then a segment determines a line, or you could think of it the other way around. 2 points determine a line, and then you can take any piece of the line in particular, just the segment, the piece that's between A and B, and that's a line segment. So they kind of go back and forth. Okay, so a piece with finite length is a segment. A piece that goes on infinitely in both directions is a line. Okay, now we have something kind of in between too. We can have one endpoint that is fixed, that's just a point, you can't go past it, and then another endpoint that determines the direction, but then allow the ant to keep going in that direction infinitely, and then it can come back. Okay, think of it as half of a line, and that's a ray. All right, now the notation for array is a little tricky, so bear with me here. So the bottom is a ray. So let's look at the red ray at the bottom first. Okay, so starting at A, the ant can go through B. Okay, I'll make it blue instead. Okay, the ant can start at A, go through B, and keep walking. Okay, that's ray AB like this. Okay, And generally speaking, the notation for arrays, we always put the starting point on the left and the point that you can go through and keep going on the right, even when we're going the other direction. So let's look at the yellow array. So now let's start at B and let's walk to the left. Let's hit A, but let's keep right on going right through A to infinity. Okay, so again, we started at B, we went to A, so that's the second point, and the arrow, the notation, points to the right, even though when we look at the diagram, the arrow up here points to the left. And again, don't let that confuse you. Okay, it's just the way we name arrays. So when we name arrays, the standard way to name arrays is to always have the arrow point to the right. Okay, and so the first letter always is where you start, and the second letter is where you march through and where you keep going. Okay, now let's look at the notation one last time. The notation for a point is usually just a capital letter. If you have several points, you separate them by commas. Okay, for a segment, line, or array, the notation is actually pretty straightforward. It's exactly, the notation is the two letters that determine whatever segment, line, or array, in other words, determine the line part, okay? And then the symbol that goes over top is exactly what it is. So if you want to talk about a segment, you put a segment bar on the top, okay, of the two letters. If you're talking about a line that goes between A and B but it keeps going, you put a line with two arrows on the top. And the same thing with array. All right, now one thing I will concede, over here on the left, if you ever saw somebody write the letters A and B in this order, but the arrow kind of points backwards, well, all right, think about what that symbol means. It still means start at B, go through A, and keep going. And this, some people do this because that way the notation kind of points in the same direction as the diagram does. But this is not the standard notation over here. Okay, just don't let it confuse you if you ever do see that. But again, this yellow one really should be written like this. Okay, I think that's where the video, if you watched it the first time, cut off. So let's continue just a little bit more. If we take this idea of the ant, so when the ant lived on this little exact location, he had 0 degrees of freedom. All right. If we allow him to move back and forth on a segment, or we can let him go walk back and forth on an array or on a line, he has 1 degree of freedom. He can basically go back and forth on a number line. All right. Now, if I take that idea and I stretch it in both an x and a y direction, so we think in ordered pairs, we're going to get a surface out of that. So think of a line, instead of going infinitely just out in 2 directions, imagine taking the line and stretching it wide to make like a piece of paper. But don't think about a finite piece of paper. Think about that piece of paper keeps stretching, 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 stretching. So first it stretches out to be like the size of the ceiling over the room that you're in right now, or over our classroom. But then it keeps going even when it hits the walls. Okay, so a flat surface that stretches infinitely in all directions, that is a plane, and that is 2 dimensions, because now the little ant guy, he can walk back and forth, but he can also walk this way. So he can make circles. He could walk around in squares. He can make all kinds of little amoeba shapes and wander all over. It might be a polygon, or he might just kind of wander. Okay, but that would live in 2 dimensions. Okay, so, and again, that's a building block. So we started with the simplest thing, a point. We built up to segments, lines, and rays that were 1-dimensional objects. Anything that lives in a plane, so polygons and circles and figures and the plane itself, are 2-dimensional figures. And then if I want to stretch just a little bit further, think about the plane rising up out of a flat surface and becoming the 3-dimensional space that we actually live in. Okay, and then if you're thinking about the poor little ant again, so this is an ant, like a female ant, that actually has wings. So not only can it walk all over the place, left, right, up, down, it can actually fly up into the air. Okay, and so now it can cover all of 3 dimensions. Okay, so that really is the building blocks for geometry. Now let's talk a little bit about when lines lie in a plane, and I'll just try to wrap this up real quickly. If lines are in a plane, you only have 2 choices. Either they're going to be parallel, which means they're going to be flat in the plane and they're never going to touch, or they're intersecting. Okay. Now you might think, okay, well, wait a second, couldn't I draw lines like this? They're not parallel, but they're not going to intersect. Well, if they're lines, they will eventually intersect. You don't see the intersection, but remember, lines go infinitely, so eventually if you stretch them back out, they will cross somewhere, even if you don't see where it is yet. Okay, so in a plane, all lines are either parallel or they're intersecting. That's the only choice. Okay. However, in 3 dimensions, and the only way I can really draw this, I have to draw an optical illusion here. So I'm going to pretend that we've got a box here. Okay, in 3 dimensions, I could have lines. So imagine a box sitting in front of you. I could take this line right here and turn it into a line, Okay, so it actually kind of goes like that. Okay, and then I could take this line over here. Okay, and while in this two-dimensional picture, obviously this line is going to come and they're going to cross each other. But if you think about this as actual sides of a box, okay, those two yellow lines, if you're in 3 dimensions, are not going to be parallel, obviously. They're not going to be the same distance apart all the way, through infinity. But they're also never going to actually touch each other. And the name for that is skew. And we'll practice that a little bit more in the classroom. It's a lot easier to see in real life because all I'm doing here is drawing an optical illusion to try to show you what skew lines look like. Okay? All right, well, we hit the 10-minute mark. For those of you that watched the first video and came back and watched this one anyway, thank you very much for your effort. I very much appreciate that. And so, signing off for 9-1, this is a great introductory unit to what we're going to be working on through the next chapter with spatial reasoning and geometry. So thanks for tuning in, and I will see you in class. Take care, everybody.